to the organizer for the invitation. I'm very glad to give a talk here. I was raised, I grew up 20 kilometers away from the Basque Country on the French side, and all my Basque friends joined me to say you Egun Hon. Oh, good afternoon. So, yeah, if I put the slides, it's better. Moderator? Sí. No? Okay, I think it's no. Gracias. So I would like to discuss about some aspects that have not been developed yet about what we call today the Hartree-Fock Method. It was elaborated in 1928 by Douglas Rainer Hartree, and it was improved in 1930 by Vladimir Fock. And it is well known that the method was only used extensively at the end of the 50s. To explain the delayed acceptance of the method, the only problem of heavy calculation and numerical complexity is often invoked, a problem solved by the apparition of computers. However, I want to show here that this exclusive argumentation can be nuanced by the addition of different factors, including conceptual difficulties that from the 30s to the 50s prevent the method to get general recognition and an extensive application. So first, I will present you the method through Hartree's and Fock's contribution. So Hartree published in 1928 an article whose aim was the resolution of the Schrödinger equation for the many-body problem. This article took as fundament the idea that without knowledge about the behavior of electrons in an atom, it is possible to consider that they are moving in a central non-Coulomb field of force. So the main approximation, because the whole concept of orbital take here the sense of quantum states represented by a wave function, the main approximation is that the Schrödinger equation for the system is replaced by a product of one-body wave functions for a central field for each electrons. It is then necessary to find the field able to reproduce the distribution of charges and then to solve the Schrödinger equation. So initially, you take an initial field. It was often chosen referring to previous studies like those based on the Thomas Fermi model. And then you correct that initial field for each electron. The electron does not act on itself. You calculate the solution of the wave equation and a new distribution of charges. And from that new distribution of charges, you can have a final field. If the final field equals the initial field, and you can do many iterations, then you have a self-consistent field. And we are interested by this self-consistent field, which is specific of the atom study, and involving no arbitrary function or constant. It is the best approximation for the distribution of charges. Then, with Hartree, the method was naturally named the self-consistent field method. This technique to find the final field will mostly remain the same in the further developments. And considering that at that time there was nothing equivalent, the first results obtained by Hartree with atoms of helium and rubidium were quite encouraging. However, the method was quickly the object of several critics. It was considered as based only on arbitrary and qualitative arguments or on the agreements between calculation and experimental results. It was qualified as semi-empirical. Then, a better theoretical basis was needed, and Dirac and Slater made two suggestions in 1929 for that. Dirac considered that the structure of the energy was not explained by the self-consistent method. So he wanted to introduce the quantum exchange phenomenon to solve that problem. The quantum exchange phenomenon is based on the idea that two electrons, being indistinguishable, may exchange place with energetical consequences, and it comes from the Pauli principle. The second suggestion by Slater was to link the self-consistent field method to the variational principle. But Slater did not really put his suggestion in a formal form, and it was overshadowed by the contribution of Vladimir Fock, who in 1930 published a very technical article based on the same idea developed independently. So Fock agreed with the idea that despite its good accuracy, the self-consistent field method was not clearly linked with the real Schrödinger wave function. And then it was possible to challenge its physical legitimacy. So while it is possible to derive the Schrödinger equation from the variational principle, Fock did the same operation for the Hartree equation. But Fock also noticed that Hartree equation did not respect the Pauli principle, which is mathematically expressed by the necessity for the equations to respect a strict antisymmetry. Then, for Hartree, well, we have the case of a product of n individual wave function to represent the general system. Fock chose a system, a product of two determinants to respect the strict antisymmetry. Fock's choice of two determinants was inspired by previous work by Hund and Heitel. And later, better expression will be done with the Slater determinant that Slater developed in 1929. So in Hartree's case, the variational principle can be expressed as a sum of individual functions for each electrons. And after integration, you obtain the Hartree equation, which looks like a Schrödinger equation with V minus J, which is an auxiliary potential. V is common for all the electrons, and J is a correction on the fact that the electron does not act on itself. In Fock's case, it's not possible anymore to express the variational functional as a sum of individual functional for each electrons. So after integration, you will obtain a linear combination of individual wave function. We can see here that we have terms in Psi and in Pk. The second term is the exchange energy term, as was suggested to include by Dirac. But you can also see that we have two different equations for Fock, and it can be explained by the fact he adopted a strict separation of variables. So we have, after separation of the spin and the space, we have spin waves and space wave. So like we are not in a relativistic case, you can just calculate the space wave. And the Pauli principle says that two electrons with a different spin can have the same wave space. So the first equation corresponds to a state occupied by two electrons, while the second one corresponds only to a state occupied by one electron. That introduction of the quantum exchange energy in the equation, starting from the variational principle, really gave to the self-consistent field a strong theoretical validation. In 1932, Tam and Bloch-Hintzeff were the first one to call it the Hartree-Fock method. But for various reasons, we will long keep the distinction between the Hartree and the Fock equation, both being used in parallel. So at the beginning of the 30s, we can consider that physicists had the possibility to do approximate calculation for the many-body systems. But during that decade, we can notice that they were done principally, if not only, in Cambridge and Leningrad around Hartree and Fock. Hartree was principally working with William Hartree, his father, and Fock with Maria Petrashen, who were in charge of the numerical calculations. However, the fact that the calculations were done only in those two centers marks the difficulties for the method to spread and interest the scientific community. To show that conceptual aspects can be added beside purely mathematical ones, to explain that problem, I proceeded from a systematic analysis of the articles published after its elaboration. Those articles came principally from Cambridge and Leningrad, but also from the specialists of the solid-state theory, who, as we are going to see later, played a particular role. I noticed in the article that many improvements were discussed as answers to various critics. Those critics were dealing with mathematical difficulties, of course, but also physical problems. For example, the French physicist Léon Brion was primarily dissuaded by mathematical difficulties. When I examined for the first time Fock's equation, they seem to me so complicated that their practical use seems very difficult. But there is something else in Brion articles. I had also to resume very closely the discussion of the basic postulates that the authors, he was then speaking about Fock and Dirac, had neglected to precise and where there were serious difficulties. And these statements are really surprising and especially motivated me because Fock is known for being a very rigorous scientist and for giving a special attention to the definition of concepts and the manner to define the problem. But Brion's critique was justified, as proves us a new version of Fock's article published in Russian in 1961, where special attention to original postulates and definition was given. Then, in 1930, many obscure points needed to be lightened. I want to focus on two aspects that show that the method really needed improvements before to spread out in the scientific community. First, the manner how it dealt with valence electron and the phenomenon of quantum exchange. So as valence electrons, I consider the electrons composing an incomplete external orbital which intervene in chemical bonds. This is then an equation particularly important for the method to be applied to chemistry and solid-state physics. The manner to treat them was the object of different articles very quickly, as with McDougall and Hartree, which were trying to explain differences between calculated results and the experimental results by the interaction of the valence electron with the core. This is called screening effect. But both McDougall and Hartree works were based only on the self-consistent field method without exchange. But McDougall raised the point that Fock's equation with exchange could be of particular interest for that problem. Of the point mentioned above, which might account for the outstanding discrepancies, the use of the Fock equation is probably the most important. Indeed, like I said, we have two different equations, one which represents a state occupied by 2 electrons, and the other one, a state occupied by 1 electron. And in a simple physical problem, if the space wave is occupied by only 1 electron, it generally describes a valence electron. In Fock's case, if you calculate the total energy matrix for each electron, the non-diagonal terms are much more better compensated than in Hartree's case. So the diagonal terms give us a good first approximation of the total energy. Then we can easily calculate the ionization potential, which is a very interesting value in chemistry and solid-state physics. Then, in first approach, Fock's equations looked very convenient on that specific subject. But in reality, due to the lack of results and interest of the community, 10 years were necessary to denounce that it was true only for univalent atoms. So it occurred in 1930 with an article by Fock, Veselov, and Petrosian, and they recognized that with many valence electrons, the situation was much more complex and that the calculations were not satisfying. In introduction, the phrasing of the article is even quite alarming. They are dealing with the limitation of the existing approximate method, or even a complete rejection of the 1 electron wave function in atomic calculations. So the problem was that the presence of 2 valence electrons or more violates the spherical symmetry. Then the 1 electron function cannot be used anymore for the valence electron. Then the author developed an improvement of the method by rejecting the approximation of 1 electron states for the valence electrons and by preserving it for the core electron. And then they added a new antisymmetric and linear term for the valence electrons to the term of the Fock equation for the core electrons. That was only a partial solution, and the most important is that it shows us that 10 years were necessary to take a look at a very crucial problem. Let's now deal with the element we watch at the same time the most important and the most difficult of Fock's improvements, the quantum exchange phenomenon. In 1932, Léon Bruyère put forward another aspect of Fock's equations which was disturbing for the physicists. So following Hartree, we write for each electron an ordinary Schrödinger equation where we introduce an auxiliary potential P, so V minus G. That definition by Hartree has a clear physical meaning. It looks like a Schrödinger equation. Fock, as a contrary, takes for the ensemble of the electron a system of simultaneous equations which is not of Schrödinger type. It is not possible anymore in this condition to attribute a simple physical meaning to the diverse interaction term. So it comes from the fact we have terms psi and pk, and that second term, the quantum exchange phenomenon, was particularly disturbing for the physicists. And there was interrogation about its meaning and its legitimacy. So yeah, I will discuss Hartree's attitude in comparison to Fock's attitude in the 30s about that problem. The British was engaged in the 30s in calculation for various atoms. However, in the first time, he used only his own equation without exchange. To explain that he was not using Fock's equation, he primarily invoked the numerical difficulties. But there is another element which is also recurrent, the notion of satisfactory agreement between the results of calculation and experiment. And actually, it was a way for Hartree to express his skepticism about Fock's improvement. And dealing with the results about oxygens, he declared that a better result would hardly be expected even if the latter two approximations were not made. That would be the case if the one electron wave function were calculated by the solution of Fock's equation instead of by those of the self-consistent field. And it seems satisfactory that the differences between calculation and observation are not larger. To me, Hartree's physical requirements were clearly under a virtual limit that we can draw between the self-consistent field with and without exchange. Then it was logically Fock with Marie Petrosian who were the first to proceed to calculation with exchange. They published their results about sodium in 1934 and about lithium in 1935 and delivered at the same time new tools to facilitate the calculations. Then it may have encouraged Fock to experience it. He published results, may have encouraged Hartree to experience it. He then published results with exchange for beryllium. However, we can notice a big difference in the way they consider their results. So, based on their articles, I imagined a dialogue they could have together. And I'm sorry, I cannot do the Russian and the British accent. So we have, on one side, Fock, who was aware about that his improvements were not really accepted by the scientific community, so he was thinking, let's advocate for the self-consistent field with the exchange. Hartree on his side was thinking, okay, I tried Fock's equation, but I stay really skeptical about their interest. Fock began to say to Hartree, Douglas, have you seen 90% of improvement in the value calculated with exchange for the valence electron of sodium and lithium? That's really amazing. And Hartree answered, but the calculated ionization energies are only 20% better for beryllium. That's really ridiculous. At that time, Fock could have answered to Hartree, yes, but beryllium is a bivalent atom. This is where the problem comes from. But he was not aware about that problem. So he was trying to find other arguments. That's still a better value than without exchange. But I also consider that a theoretical determination of a given physical property of an atom can be given by its calculations by means of the mathematical method of quantum mechanics. Then the Hartree-Fock method is a theoretical determination of the transition probabilities. And Hartree, answering, I cannot agree. If the energy value is used as a criterion in judging the importance of the various approximations made in the self-consistent field, or for the best wave function, the neglect of exchange is not the most important of them. Vladimir, your contribution is not that crucial. And if you listen to that or read the articles, as an historian of physics, you can add a bubble and think that as a founding father, Hartree should have played an important role in the acceptance of the Hartree-Fock method. But it did not, because it was skeptical. So, in general, Hartree's article just continued to raise questions concerning the criteria necessary to validate the method, to judge it satisfactory, and so on. It is probable that Fock shared most of those interrogations, and he delivered in 1936 an enlightening and modern point of view on the fundamental significance of approximate methods in theoretical physics. The initial claim of Fock was that equations of theoretical physics can never be absolutely accurate, and that the essential factors for a physical problem can be combined under the idea of physical rigor. As he said, one of the most important and difficult questions in each field of theoretical physics is to what extent the requirements of physical and mathematical rigors are satisfied when the problem in a given field are posed and solved. Then the physical rigor of a problem is related both to the validity and the applicability criteria of an approximate method. Concerning the choice of Hartree or Hartree-Fock method, the error evaluation between theoretical and experimental results was an important criterion. With an error of less than 1–2% in the cases of sodium and lithium, Fock obviously considered that the Hartree-Fock method gives a precise enough formulation of the initial complicated problem raised by quantum mechanics. On the contrary, the satisfaction of Hartree with a divergence of 20% in the self-consistent field without exchange shows us that his expectations in terms of physical rigor were highly less important. However, the real object of Fock's article is to think about the formation of a physical notion. I guess it is clear for everybody that in the transition from a particular theory to a more general one, there is an introduction of new physical notions, but also a rejection of old physical notions. But maybe you did not find in those terms that in the transition, for example, from Newton mechanics to general relativity, the simultaneity becomes an approximation. Then Fock decided to follow the process of the formation of notion in the opposite sense to the historic developments of a theory, to show that for each simplification, for each approximation, new physical notions arise. In his sequential simplification of the quantum theory, he passed from the exact Schrödinger equation to the Hartree-Fock method and showed that two new physical notions can be defined. First, that electrons in an atom have individual states as well, and second, that there is a quantum exchange energy. And that quantum exchange energy is unknown both for the classical mechanics and the exact Schrödinger theory. We can connect that to the general conclusion of the article. We wanted to show that any physical theory, any physical notion, is as a matter of fact an approximation. Each with progress of physical science is related not only to the creation of new notions, but also to the critical revision of old ones. In my sense, it partially explains why the Hartree-Fock method remained quite unusual. The quantum exchange energy was both a notion which arose from the generalization of classical mechanics and the approximation of quantum mechanics. This notion had a very precarious status, and its meaning appeared very obscure to many physicists. If you remind the initial definition I gave of it, saying that it is an energy produced by the interchange of two identical electrons, you can guess that it is actually not satisfactory at all, and the physicists knew that. As Fock status, its name was only given because it appears when Pauli principle is taken into account. Fock considered that because it was a quantum phenomenon, it was difficult to give it a visual interpretation and a denomination. However, it did not went further in this reasoning. But the posterity of the method was depending on the capacity of physicists to give to the quantum exchange phenomena a better interpretation. And if I mentioned the physicists working on the metal theory before, on the solid state theory, it is because they were those who brought the solution. And among them, I include John Slater, who, inspired by previous work by Briand, Wigner, and Seitz in the 30s, gave to the Hartree-Fock method a new and crucial impetus. But it happened only during the 50s. After that, he organized at the MIT a small research group called the Solid State and Molecular Theory Group. The object of the group was to take the quantum theory of atoms, molecules, and solids out of the semi-empirical form which it has largely followed since the development of wave mechanics, and to proceed as rapidly as possible to put it on a quantitative basis. For that project, it chose the Hartree-Fock method as a starting point. And Slater called for a close examination of the meaning of the equation to see physically how to set up a simplification applicable for heavy atoms, molecules, and solids. And it happened in an article of 1951, called A Simplification of the Hartree-Fock Method. In that article, Slater tried to give a precise meaning for each of Fock's equation terms, and especially the exchange energy one. He considered that it must somehow correct for the fact that the electron does not act on itself, which it would be doing if this term were omitted. In the Hartree as opposed to the Hartree-Fock equation, this is obvious. Fock equations for Slater are an ordinary Schrödinger equation for an electron with a spin moving in a perfectly conventional potential field corrected for each electron. But the novelty is in the correction. Here, the correction takes the form of a deficiency of charge, which can be assimilated to a charge hole, depending on the spin and the specific atom. And it equals the value of the electron charge at its position and follows gradually with distance. Then, to set up a simplification, Slater proposed to introduce an average exchange hole for all the electrons. Nevertheless, the results of Slater still presented numerical difficulties. But he was aware that at the beginning of the 50s that the new digital computers, just beginning to be developed, would probably be able to make the method practical for complicated cases. Indeed, in the late 50s and early 60s, the greatest activity on the atom came with extensive Hartree-Fock calculation that were applied to the computation of X-ray form factors, superfine interaction constants, and so on. This is actually a sign that the development of computer was necessary for an extensive use of the Hartree-Fock method. But I wanted to show, and I hope that I convince you, that before the 50s, the method was simply not ready for an extensive and satisfactory use due to several conceptual problems. The article of Slater marked that switch from a situation where the method was not ready for physicists' mind to another one where computers were not ready for the mind's requirements. The simplification of the Hartree-Fock method by Slater will later be called the X-alpha method. And it marked the beginning of diverse developments that will be classified as post-Hartree-Fock methods. This is why I consider it as a real boundary, but I guess that after the break, my colleagues will speak about the post-50 periods and the quantum many-body problem. Mileška.
Well, thank you for the talk. Andrew?
Thank you for this nice presentation. You're quite right that the exchange term was mysterious. But I don't agree that that mystery is what kept people from using it. I don't think you can find anywhere in the literature, except the occasional remark by Brillouin right at the beginning, where people say that that's keeping them from actually applying it. The numerics was horrendous. And even in Hartree had good reason to defend his own method. He derived his equations heuristically. In fact, they weren't derived at all. They're written down heuristically. Whereas Fock actually derived them from a variational principle. Slater recognized that instantly in 1930 already. And he was already saying that this is the way to go. But the numerics were very difficult. It's much easier to solve the Hartree equations than the Hartree-Fock equations. So if you could avoid them, you did. And it's also true that Slater explained the physics of the exchange term, just as you say. But I don't believe that it was a conceptual problem. I think it was simply too hard numerically. You had to commit. Hartree committed his entire career to solving these equations. Fock immediately went on to other things. So I'm not certain you've made the case that other physicists stayed away because of conceptual problems.
Yeah, I did not want to say there wasn't numerical difficulties. I think it was more a combination of both problems, numerical and conceptual, that kept away physicists to work on it. And I don't know, maybe I'm naive about that, but I think that if it was really working, physicists had PhD students to do the calculations. So I think it's really a combination of both problems.
Next will be Alex.
Thank you. That was very interesting. I wanted to ask you on that paper by Fock where he discusses the approximations in physics. I didn't quite. So this point of new physical concepts emerging when you go to approximations. That's also a point he makes in that paper. Is that?
Yeah.
Yeah. And does he actually use the Hartree-Fock method as an example for that in the paper?
Yeah, exactly.
And what other examples does he bring forth there?
It's really a sequential simplification. He's going from electrodynamics, and he makes a simplification through mostly of his works, second quantification, Hartree-Fock method, mostly those two examples.
Okay, but the paper is translated in his collected papers?
Yeah, and selected works.
Yeah. Okay, good. Then I can read it myself.
Tony, next one.
The problems with divalent atoms were recognized, well, that the method was not as successful. Of course, it's partly the problem of the central spherical symmetry. It's now known as a theorem, right, that the effective potential for closed shell or half-closed shell atoms is rigorously spherically symmetric in the Hartree-Fock approximation. But when was this actually understood? Did that take till Slater? That you can prove that the spherical symmetry is holes for closed shells, and therefore one more valence electron doesn't see itself, but sees the closed shell, and therefore spherical symmetry is still okay, but not two more.
Yeah.
When was that really first understood?
From what I have seen, there is only that article in 1940 by Fock, Veselov, and Petrosian, and there is nothing clear about that before. It's I was surprised.
Modern texts, that's one of the first things they prove when they're discussing Hartree-Fock is this. That, there are cases when it's not an approximation, you assume spherical symmetry for the effective potential in certain cases. Closed shell plus one valence electron.
Yeah, I don't really know.
Next question is for Carol.
Thanks, Jean-Philippe, for this very nice talk. That's the third time I see you talking about Fock, and all three times about different aspects of Fock's work. So I think that's very nice. And going into the Russian sources, and that's even nicer. So about what Andrew said, I think that's what all physicists would expect, right? That the computational difficulties are very hard, and that's the reason that prevented people from using the method. So I think it's very nice that there is also some conceptual objections or positions to the method. And I think it's, but my question is, there is one thing that we discussed it some time ago, and I'd like to know whether you found something later about that. In the 1932 translation into Russian of Dirac's book, there is some extra chapters that only exist in the Russian edition that were written by Dirac himself on the request of Ivanov. Ivanenko. So, yeah, sorry, Ivanenko. And so in that book, that 1932 editions sold 3,000 copies in Russia, in Soviet Union. So do you know something else about that? So which is the impact of that extra chapters in the Russian public? Did people discuss that because of the book? Do you know whether how Dirac reacted to this request of Ivanenko and all that? So that's my question.
Okay, I have no idea. You learned me about that story, but there is one interesting thing about that is that on the book of Fock about quantum mechanics published on the same year, 1932, there is nothing about the quantum many-body programs. So this is all what I can say.
Next one is Alexei.
Yeah, I have a small comment and a question. A quick question actually, George with the others. The comment is the way I want to explain what was mysterious about the exchange term. I don't think Fock considered it mysterious. Mysterious looked at people who thought in some kind of a reductionist terms, that basically you can reduce the many-body problem to the quantum mechanics, which is the one-body theory. And if you look at this way, yes, the exchange term is not reducible. And Fock's methodology, and kind of this is partially what that paper is about, is essentially non-reductionist. So to put it in a very simple way, his view was that many-body problem is, in a sense, a different science from quantum mechanics, or a new kind of, and it's an addition to the existing quantum mechanics, but it's not reducible in full. So to him, it would be natural to think that if you switch from quantum mechanics to the considering many-body problems, you'll get new phenomena, new notions, and some kind of new laws. And from this point of view, kind of this exchange would not be mysterious for him, but simply it's a decision from one level theory to another, with like something like mesoscopic, so things like that. And that I think was kind of the crucial sort of methodological distinction between his view on and Hartree's views on the thing. And for the question, so I also wanted to ask Dirac, because Dirac would be the good arbiter of this thing. And not only in this Russian edition, which indeed the edition was about the many-body problem, but in the subsequent editions of Dirac's book in English too, because he had a chapter, and he has an article on many-body problem around the same year. So it would be good to analyze that. What position did Dirac take on the issue?
There is a contribution by Dirac right after, and the most important fact is that he decided not to do a separation of variables. So he keeps the spin in the equations, and they are even more complicated. So this is what Briand says. He said, I have Fock and Dirac documents, and I cannot understand. They are not clearly explaining what they are doing.
But what is Dirac doing in late editions of his book?
I don't know about the book.
He always has a chapter on the many-body calculations of the Valence Electron. And I don't know whether he sort of changed his mind or changed his the concept, the Dirac's position of it from one to another.
Last question for Christian.
One quick comment on this, and then a question. The quick comment is, I'm not sure that you really need to go like towards the emergence of laws or notions already with exchange at this time. So I think if you, for instance, look at this two-part paper by Kathy Carson on the nature of exchange forces, you see that you find good explanations for how people dealt with exchange, with the exchange terms, and also exchange forces, like in, for instance, Heidler London, that do not invoke that, and it's actually quite straightforward, I think. For instance, like, let me just mention that Oppenheimer, who is certainly not somebody who would have subscribed to an emergentist point of view, considered it somehow an essential meaning of quantum mechanics that you have exchanged. But what I wanted to say is, if you look at solid-state physics in the 30s, Hartree-Fock, in a way, serves as a point of departure for yet even like more crude approximations. Did you look at that? If you look at like Wigner-Seitz or Bardeen's work or Wigner's work in the 30s?
No, not really.
Yeah. Yes.
Okay, so let's thank Jean-Philippe again.
Okay.
So we are